On Christmas Eve, 2024, while most of humanity was asleep or celebrating, a small spacecraft the size of a car did something that every physicist who came before us said was categorically impossible. It flew into the sun, not toward it, not near it, into the actual atmosphere of a living, breathing, violent star. And when it disappeared behind that wall of plasma and fire, every scientist at Mission Control could do nothing but sit in silence and wait. What that spacecraft found when it came back out is not just rewriting textbooks. It is forcing us to rethink assumptions about stars that we have held for more than a century. This is the story of what happens when humanity finally refuses to stop at the edge and decides to reach in. Here is the thing that most people get wrong about the sun. They think the danger is the heat, and technically, yes, the surface of the sun burns at around 10,000 degrees Fahrenheit. That is hotter than anything you will encounter anywhere in ordinary life. But the surface is not what keeps astrophysicists awake at night. What keeps them awake is the corona. The corona is the sun's outer atmosphere, an enormous, invisible envelope of magnetized plasma that stretches millions of miles in every direction. And the corona does something so deeply strange, so fundamentally wrong according to everything we know about physics, that scientists have called it one of the greatest unsolved mysteries in all of science. The surface of the sun sits at 10,000 degrees. The corona above it reaches temperatures between 1 and 3 million degrees, 300 times hotter than the surface directly below it. That is not just unusual, that is a violation. If you walk away from a fire, you get cooler. That is not a preference. That is thermodynamics. The sun ignores it entirely, and for more than 80 years, nobody could explain why. That mystery is not simply academic curiosity, because the corona is where everything begins. It is the origin point of the solar wind, that relentless invisible river of charged particles that flows outward from the sun in every direction at speeds between 200 and 500 miles per second. That wind reaches Earth. It slams into our magnetic field. On good days, it gives us the aurora borealis and nothing more. On bad days, it collapses satellites, blinds GPS systems, and overwhelms power grids. In 1859, a solar storm now called the Carrington event hit Earth with such force that telegraph wires across North America and Europe caught fire. Operators reported receiving messages for hours after they had disconnected their equipment entirely from any power source. The storm induced so much current directly into the wires that the wires themselves became the power supply. If that same storm hit today, some estimates suggest the damage to global infrastructure could exceed $20 trillion. Recovery could take years. The satellites we depend on for everything from financial transactions to emergency services would go silent. Understanding the sun is not a luxury. It is a survival requirement. But before you can understand the mission, you need to understand the man it is named after. In 1958, a young astrophysicist named Eugene Parker submitted a scientific paper to one of the most respected physics journals in the world. In it, he argued that the sun does not just radiate light and heat outward. It constantly exhales, a continuous stream of charged particles, electrons and protons, flowing outward through the entire solar system in every direction all the time. He called it the solar wind. The journal sent the paper back. The peer reviewer, an accomplished and well-regarded scientist, wrote that the paper contradicted established physics and should not be published. Parker appealed. The paper was eventually accepted only after the personal intervention of the editor-in-chief, Subramanian Chandrasekhar, who would later win the Nobel Prize in Physics. 2 years after publication, Early spacecraft measurements confirmed that Parker was completely right. The solar wind was real. It existed exactly as he had described it. Over the following decades, Eugene Parker became one of the foundational figures of solar science. So, when NASA began preparing to send a spacecraft directly into the Sun's atmosphere, they made a decision they had never made once in the entire history of the agency. They named the spacecraft after a living person. Parker was 91 years old when he stood on the launch pad in Florida and watched his namesake accelerate into the sky on a column of fire. He passed away in 2022 at the age of 94, having lived long enough to see his own name attached to the most daring mission ever pointed at the star he spent his entire life trying to understand. Now, here is the engineering problem that kept aerospace scientists occupied for decades. How do you build something that can physically survive inside a star's atmosphere? The sun-facing surface of the Parker Solar Probe reaches temperatures of approximately 2,500 degrees Fahrenheit during its closest approaches. That is hotter than lava. That is hot enough to melt steel, titanium, and aluminum as though they were wax. And yet, the scientific instruments sitting just 4.5 inches behind the heat shield operate at roughly room temperature, 85 degrees Fahrenheit. That gap, 2,500 degrees on one side and 85 on the other, separated by a shield you could hold under one arm, is one of the most extraordinary feats of thermal engineering in human history. The shield itself is made of two panels of carbon-carbon composite sandwiching a core of carbon foam that is 97% air. It is almost impossibly light and almost impossibly effective. The sun-facing surface is coated with a special white ceramic paint that reflects the overwhelming majority of incoming radiation rather than absorbing it. And then there is the detail that surprises almost everyone when they first encounter it. The corona reaches 1 million degrees. So, why does the spacecraft not simply vaporize the instant it enters? Because temperature and heat are not the same thing. Temperature measures how fast individual particles are moving. Heat measures how much energy actually transfers when those particles collide with the surface. The corona is searingly hot, but it is also nearly a perfect vacuum. There are so few particles per cubic centimeter that even though each one carries enormous energy, the actual heat load delivered to the shield remains survivable. The spacecraft is not wading through a million-degree bath. It is threading through a million-degree near-nothingness. And the carbon shield can handle that. Parker Solar Probe launched in August 2018, but it did not aim directly at the Sun. The geometry of the solar system makes that essentially impossible. A spacecraft launched from Earth carries too much sideways orbital velocity and would curve into a wider orbit rather than falling inward. To overcome this, NASA designed an approach using gravity assists, using the gravitational pull of another planet to act as a brake and redirect the spacecraft's path. That planet was Venus. Over 6 years, Parker flew past Venus 7 times. Each flyby used Venus's gravity to peel away orbital speed and tighten the spacecraft's trajectory around the Sun, like slowly drawing a spiral inward. With each successive orbit, the spacecraft reached a new record closest approach, a new perihelion, before swinging back outward and then falling deeper inward on the next pass. And during those years of progressively tightening orbits, the discoveries had already begun. The spacecraft detected enormous zigzagging reversals in the Sun's magnetic field lines, structures researchers nicknamed switchbacks. These appeared in numbers far beyond what any model had predicted, and they seemed to be connected in some fundamental way to the process of accelerating solar wind particles to extraordinary speeds. It flew directly through coronal mass ejections, those monstrous explosions of magnetized plasma, and measured them from the inside for the first time in the history of space exploration. The final Venus flyby occurred in November 2024. After that, there was nothing left between Parker and its destination. On the morning of December 24, 2024, the team at the Johns Hopkins Applied Physics Laboratory in Maryland was not home with their families. They were at their consoles watching telemetry data scroll across screens and waiting for the moment their spacecraft would disappear. As Parker fell toward its closest approach, it crossed into a communications blackout zone, a region so close to the Sun that the intense electromagnetic environment of the corona completely overwhelms any radio signal the spacecraft can transmit or receive. The team had planned for this. They had known it was coming for years. But there is a profound difference between understanding something on paper and living through it in real time. At a precise, pre-computed moment, the spacecraft went silent. No telemetry. No beacon. Nothing. A machine they had spent more than a decade designing, building, testing, launching, and shepherding through 6 years of increasingly dangerous orbits was now flying on autopilot, completely unreachable. At 400 to 30,000 miles per hour, 3.88 million miles from the surface of the Sun. For context, Mercury, the closest planet to the Sun, never gets within 28 million miles of the solar surface. Parker's solar probe was more than 7 times closer to the Sun than the innermost planet in our solar system ever gets. The team sat in near silence and waited. On the evening of December 26, 2024, 2 days after closest approach, a signal arrived. A single beacon tone from the spacecraft, indicating its health status. Instruments operational, structure intact, systems nominal. I am here. I survived. The room reportedly broke into tears. When the full science data began downloading to Earth in January 2025, researchers had something that no human being had ever had before. A detailed, close-range, first-person view of the inside of a stellar corona. Not from a telescope squinting across 93 million miles of empty space, but from within it, from inside the phenomenon itself. The spacecraft's wide-field imager for solar probe camera captured footage of the solar wind being born in real time, streams of charged plasma pulling away from the corona, organizing into the structured flows that eventually reach Earth and every other planet in the solar system. Scientists described the experience of watching the data arrive as something like spending your entire career studying a vast river from a bridge miles downstream, then finally, for the first time, standing at the source and watching it emerge from the ground. The entire dynamic of solar weather formation was suddenly visible, not inferred, not modeled, visible. The data also captured something that had existed only as a theoretical prediction before the mission. A phenomenon researchers are describing as a solar wind feedback loop. When the Sun launches a coronal mass ejection, a massive explosion of magnetized plasma, not all of it escapes into space. Some of it curves back toward the Sun, pulled in by the magnetic field, re-entering the corona, altering its structure, and directly influencing the trajectory and intensity of the next ejection. Parker filmed this process in intimate detail no instrument had ever achieved before. This feedback loop matters enormously for space weather prediction because it explains one of the most persistent puzzles in solar physics. Why 2 coronal mass ejections launched under apparently similar conditions can produce wildly different outcomes at Earth. The corona is not a simple cannon firing predictable shots. It is a dynamic, self-modifying system where each event reshapes the conditions for the next one. And then there is the coronal heating problem, the 80-year mystery. The preliminary data from the Christmas Eve flyby is pointing with increasing confidence toward those switchbacks as one of the central mechanisms. The data suggests that these magnetic reversals carry energy from the Sun's surface upward into the corona through a combination of alpha and wave propagation and small-scale magnetic reconnection events. When magnetic field lines that are pointing in opposite directions are forced together, they snap and reconnect, releasing energy explosively into the surrounding plasma. Parker's instruments are detecting this process happening continuously, at scales too small to observe from any distance, contributing incrementally to the enormous temperature difference between the surface and the corona above it. It is not one single process. It is a cascade of interacting mechanisms, and Parker is giving scientists the resolution and proximity to finally map it with precision. 80 years of mystery is beginning to resolve into something comprehensible for the first time. The practical implications of all of this are difficult to overstate. Right now, the best early warning systems we have for incoming solar storms give us somewhere between 15 minutes and a few hours of advance notice. That is barely enough time to put some satellites into a protective safe mode. It is nowhere near enough to protect large-scale power infrastructure. With the data Parker's solar probe is generating, seeing how solar wind structures form at the source, how coronal mass ejections evolve in the minutes and hours after launch, how the magnetic environment of the corona shapes the eventual trajectory of a storm, researchers believe we can eventually extend that warning window to days rather than minutes. That is not an incremental improvement. That is a transformation. The difference between 15 minutes and 3 days of warning before a Carrington-scale event is the difference between inconvenience and catastrophe. Parker Solar Probe continued making close approaches throughout 2025, each time matching its record. Perihelion of 3.88 million miles and its record velocity of 430,000 miles per hour. The Sun is currently near the peak of its 11-year solar activity cycle, meaning the corona is more energetic, more turbulent, and more active than it has been in a decade. And Parker is collecting data from inside it in real time through conditions that no instrument was ever designed to endure. The mission was originally planned to conclude in 2025, but given the volume and quality of data still arriving, extended operations remain under active consideration. Every orbit is another chapter of a book that humanity has been trying to read for thousands of years, finally being written in a language we can understand. For all of recorded history, the Sun was the one thing we could never touch. Every ancient culture that looked up at it knew instinctively that it was beyond reach. Too powerful, too distant, too absolute. A force that gave life and could end it, and that would never be grasped by anything human. We built mythologies around its untouchability. We drew it on cave walls and worshipped it in temples and tracked it in stone monuments. And for the entire span of human civilization, that instinct was correct. It was beyond us. And then, on December 24, 2024, we reached in anyway. We built something extraordinary enough to survive the thing we were most afraid of. And what we found inside that star is not terrifying. It is illuminating in every sense of the word. It is telling us how our star works, how to protect ourselves from it, and perhaps most importantly, it is telling us something about ourselves, that there is no frontier we will ultimately accept as permanent. No boundary we will not eventually cross. No star we will not eventually touch. The question worth sitting with is this: if we can build something capable of flying into the atmosphere of a star and surviving, if we can reach into the most violent environment in our solar system and pull out answers to mysteries that defeated every generation before us, what exactly are we still telling ourselves we cannot do? Subscribe if you want to keep asking that question.